what we've got here on this slide is the question, what makes a light bulb glow? So let's give this a quick read here and figure this out. Inside a light bulb, you can see a filament, which is part of the closed circuit. When electrons flow through the filament, the electrical energy is converted into thermal energy. The thermal energy is then converted into radiant energy, and of course the radiant energy is the light that lights up the room. Okay, so let's look at the light bulb over here. First of all, it's important to know that this is an incandescent light. This is the type of light bulb that Thomas Edison invented. These incandescent light bulbs. This is your classic light bulb. They're not as common these days. In our classroom, we have fluorescent lights. They work a little bit differently. The electricity excites a gas that gives off radiant energy. We have light-emitting diodes, LED lights, that are becoming very common. But this is your classic style light bulb right here. And the way it works, if you think about it, what's basically happening is that when you plug a lamp into the wall, you notice that the cord for the lamp is fairly thick, and a lot of electrons can move through that wire inside that electrical cord. Notice, though, that the filament inside the electric light bulb, this area right here, these little wires, those are very thin. So you plug your lamp into the wall, a lot of electrons move through those wires, but then they get all jammed up in this thin little filament here. So the electrons move through that filament, and they get all jammed up. And because the filament is very thin, it has resistance to the electron flow, and that resistance creates a lot of heat. That's why the light bulb gets hot. And it gets so hot that it starts to glow, and that's what gives us the radiant energy. So the resistance of the electrons flowing through the wire causes a lot of heat. It causes so much heat that the wires begin to glow. They get so hot, and that's what gives us the radiant energy. Now, Thomas Edison invented the light bulb. What his key invention was not the idea that things glow and give off light when they get hot. People knew that long before Thomas Edison came along. What Thomas Edison's genius was to find a material for this filament, for this little area right here, this very thin wire that glows. He found a material that would last long enough and not burn up. It would last long enough to make a practical light bulb. He literally tried thousands of different materials, and eventually he found something. He and all his lab workers eventually found something that could have electrons moving through it and get so hot that it glowed, but it would not burn up immediately. And that's what made the first practical light bulb. Okay. Now let's look at our next slide here. This is about resistance. Resistance is the tendency of a material to oppose the flow of electrons. When electrons encounter resistance, that electrical energy is converted to thermal energy, and then that thermal energy gets hot enough can become radiant energy or light. Over here on the side, when you look at electrical circuit diagrams, this wavy line right here, this is the symbol for resistance. So when you look at a schematic, an electrical schematic, if you see this indicates that there's resistance in that line. And then the Greek letter omega right here, this letter, this is the symbol, also the symbol that's used for resistance in equations. Now, all materials have some electrical resistance except for a superconductor. What a superconductor is a material that electrons can pass through free of resistance. And the only superconductors that we know about work at extremely cold temperatures, temperatures that are approaching absolute zero. And in those materials, electrons can flow freely, and there's no wasted energy. If we had superconductors that didn't need to be cooled, that could work at room temperature, that would revolutionize our world. We would have it would solve all our energy problems. But right now, the materials that we use to carry electricity are not superconductors. And a lot of that electrical energy is wasted because of resistance. The resistance converts that electrical energy into thermal energy, which we usually don't need. What we want is the electrical energy. Now, resistance is measured in ohms, okay? So the Greek symbol omega is used for ohms, and ohms is the unit that we use to measure resistance. And the resistance of a wire depends on the temperature, the length, and the thickness. So let's talk about each of these very quickly here. As I said, temperature has an effect on resistance, and the superconductors that we know about with our present technology only work at extremely cold temperatures. But you can reduce resistance to electricity by reducing the temperature. It slows the particles down, allowing the electrons to jump more freely. The length of a wire also affects the resistance. The good example that I can think of this, that an everyday example, is that sometimes you work outdoors with, you guys have probably all seen electric hedge trimmers and electric leaf blowers and things like that. And you have, nowadays, a lot of times they're battery powered, but you still can buy and you still see people using them, leaf blowers and hedge trimmers with a long electrical cord, and that cord can be 100 feet long. What happens when you have a cord that long, it has a lot of resistance, and if you're using your hedge trimmer with a 100-foot electrical cord, if you grab the electrical cord after it's been running for a while, you'll feel that that cord really gets kind of hot. And that's because of the resistance of that long cord slows the electrons down. The other thing that affects the resistance is the thickness of the electrical wire. And you look around your house, if you look at things that use a lot of electric current, that need a lot of electrons to operate, like an electric dryer, you'll notice that the cord is very, very thick. Same with if you can see the power cord for if you have an electric oven or electric stove, it's a very, very thick cord because it carries a lot of electrical energy, a lot of electrons move through that. On the other hand, some wires are very thin, like the wire to charge your cell phone is very thin. That's because those devices operate with fewer, they don't need as many electrons to move through the wire. So resistance of a wire, it depends on temperature, length, and thickness. You have more resistance at higher temperatures, you have more resistance with longer wires, and you have more resistance with thinner wires. You can't force as many electrons through thinner wires. Next topic is Ohm's law. And Ohm's law shows the relationship between voltage, current, and resistance in a circuit. Okay, and Ohm's law, what it states is that the current in a circuit equals the voltage divided by the resistance. Okay, so excuse me. Here is the equation for Ohm's law. Okay, I is the electric current. I don't know why I is what stands for current, but that's what it is. V is the voltage, and R is the resistance. Okay, so this is Ohm's law, and then here's one of these little triangle things where you can figure out how to algebraically manipulate it. Now, on the next slide, here are some Ohm's law practice problems. We're not going to spend a lot of time on this, but it's pretty easy. The first one, find a current for a circuit which contains a resistor of 459 ohms connected to a 28-volt power supply. Here's your equation. Okay, you're looking for I, you're looking for the current. The voltage is 28 volts. The resistance is 459 ohms. Okay, so if you solve that, your current is 0.061 amps. Amps is what's used to measure the current. Here is Ohm's law again. Now you're going to solve for resistance. Okay. So here's your voltage, here's your amperage, and you can figure out 1.1 ohms. Okay. And down here, you're solving for voltage. Okay. By algebraically changing it. Now, Ohm's law, um, some of you might want to make a note of this. This is something that's very useful and very practical in everyday life. Give you a quick example. When I got my first car, it would have been 42 years ago. I got my first car. Like guys back then and like guys now, one of the first things we want to do is add some really loud speakers to our car because guys, one thing we like to do is we like to take our money and turn it into noise, right? So one of the first things I did when I got my car was add a powerful amplifier and powerful speakers so I could play music really loud in my car. And what I found was that the amplifier that I needed to run these speakers drew too much current and kept burning out the wires. So I had to use Ohm's law to figure out what types of fuses I needed, how thick the wires, what the resistance of the wires had to be, and so forth. So I could figure out how to use the amplifier in the car to power the speakers that I wanted to. Uh, today, now I'm not so much interested in, playing loud music in my car, but I am interested in working on my house. And again, I can use Ohm's law to figure out if I want to add a ceiling fan or add an electrical circuit in my shop. I can use Ohm's law to figure out what type of resistance I'm going to encounter if I run depending on what devices I want to run. So Ohm's law is something that's very practical in everyday life.